I just fixed that. So, okay,
Okay,
that
okay.
second technical issue is fixed. So we are pleased to have Mate joining us from Vienna, who will be speaking about variance renormalization and singular SPDs. And usually we have a break in an intermediate break in the presentation to kind of ask questions that come up. So whenever you feel like you've hit a point in your presentation, somewhere close to halfway through, let us know, and we'll do one question period before doing question again at the end. So yeah, thanks, and yeah, start whenever you want.
Perfect. Thanks for the introduction and thanks for inviting me to this nice new initiative. I'm happy to be here. Yes, so I will talk about variance renormalization, which is I kind of used it as a synonym for variance blow-up for a while, but in particularly for this talk, maybe this distinction will start making more sense because it will somehow, the two types of results that I will get to, in one of them, the variance really does blow up, and that's what has to be renormalized. And in another example, the variance actually somehow vanishes, and that has to be renormalized. And it's an overview of a couple of works. Most of it is finished, and one of it is in progress, but close to being finished, and the co-authors in the different works are listed here. So starting, I will start somehow. So yeah, so these two parts that I mentioned, and I think this will be probably the break will be between these two parts. And the first part will be really what is also referred to as variance blow-up. But I will kind of start from a bit earlier and more classical things. And yes, so I'll just start to review a few classical things about the KPZ equation. This will be somehow the main example. We will see some other singular SPDs along the way, but KPZ, we will return to it again and again. So in the very classical case, KPZ equation is a nonlinear equation driven by some random term eta, which often one takes it to be space-time white noise, but for now I will just take it to be a general random field with regularity alpha, and typically random driving field will be a distribution, which means it has negative regularity. And as long as the negative regularity is even less than -1, then we have this well-known problem that the nonlinear term is ill-defined in a classical analytic sense. And if you do very naively, you just want to make it well-defined, so you regularize the noise by some modifier, and you replace the noise by the modified noise. Then, of course, no longer you have a problem with defining what the square is, but typically you will not have a limit as epsilon goes to 0. So as you want to remove the modification and make sense of the original equation, this does not work. And in the interesting case, which is the one that in the original KPZ paper was considered, we are in this regime. So if the eta is space-time white noise, so for me, psi will be, I try to be fairly consistent, and I hope I managed to be fairly consistent with the notation. So psi will always be white noise. In this case, space-time white noise, then its regularity is minus spatial dimension plus 2/2, and already in dimension 1, this is, of course, in this regime. And then the way this problem is dealt with is an additive renormalization in dimension 1. So in dimension 1, the following theorem goes back to the breakthrough of Martin Heider no more than 10 years ago. That if you don't take this equation with just modifying the noise, but you insert a constant which diverges and diverges at the correct speed, then you do get a non-trivial solution. And in fact, you can choose it in a way that the solution does not depend on the modifier. And moreover, it actually agrees with the call of solution, which is another way of making sense of the original equation. Okay, now since then there has been a big black box of developed under the name of theory of regulative structures, which tells you that actually the fact that it was spacetime white noise in one dimension in the previous theorem is not somehow the theorem holds in a more general setting. So for example, if you take a Gaussian at a with certain regularity, then it as long as the regularity satisfies certain constraints, then basically the same theorem holds. And there are two main constraints. One is the most well-known, the subcriticality constraint, which in this case for the KPZ equation asks that alpha should be bigger than -2. So this is what I will denote by alpha c, so the critical exponent for scaling. And you can find this exponent by trying to rescale your equation. So you rescale it, you try to zoom in into small scales. So you take a small lambda and you take the lambda, so you take the rescaling, first of all, in a parabolic way, and secondly, in a way such that the noise does not change in low. So this fixes all your choices of exponents. And then you pick up a factor in front of the nonlinearity. And as long as the subcriticality condition is satisfied, this exponent will be small. The exponent will be positive, so the prefactor will be small. So on small scales, the nonlinearity is less and less important. And there is another constraint, which is less well-known, which in the paper by A.G. and Martin is referred to as superregularity. I don't know if this comes from anywhere, but okay, this is how it's denoted there, which in the case of KPZ equation reads like this. So it's alpha bigger -3/2 minus d over 2, d over 4. So first of all, notice that the first scaling argument did not depend on the dimension. This second exponent does depend on the dimension. So this I will denote by alpha v as kind of, this will be related to the variance business. This is why v. And this is what we will explore in a bit more detail. But before, just so that a quick remark why perhaps this is less well known, that as long as we are in the spacetime white noise case, which is alpha, again, is this minus d plus 2 over 2, then actually the two conditions each of them are only satisfied in dimension 1. So kind of one can easily forget about the second. Okay, so what is relevant about this alpha v? So let's go back and let's take the driving noise to be a typical regularity alpha Gaussian field. So for example, you can take your spacetime white noise and apply amount of derivative. Maybe there's a typo here. I think this should be probably an alpha over 2. But okay, you just find the correct exponent of a derivative that makes you moves you from regularity minus d plus 2 over 2 to alpha. And let's start looking at the Picard iteration of the equation. So this is how one could start trying to make sense of the equation. So the first Picard iterate is just the heat kernel. I take it to be, for simplicity, the massive heat kernel, but this is technicality. You basically take the heat kernel convolved with the noise. So this is the first Picard iterate where the nonlinearity is not there. And then you want to start doing the Picard iteration. So you want to plug this first Picard iterate into the equation, for which you have to take its derivative. This is what we denote by z, and you have to take the square of it. So this would be the z epsilon squared. And okay, we already know that this is not expected to converge on its own. This has to be renormalized. So if I take a nice test function phi, and I put it into this renormalized z epsilon squared, then as long as I'm in the alpha bigger alpha v regime, then this converges. So there is this additive renormalization is there, so something divergent is subtracted, but then the resulting fields, which are then random distributions, all belonging to the second Wiener chaos, they converge to a limit. Now, on the other hand, when alpha is less or equal to alpha v, then they do not converge. Simply already I mean, you can just compute their variance, and the variance blows up. So this is the variance blow up from the terminology. Now, on the other hand, this is still a fairly simple object. So this is something in the second chaos with a very explicit kernel. So you can just pretty easily compute the speed with which it blows up. And for simplicity to not deal with logs, I will now assume strict inequality in the alpha less than alpha v. Otherwise, the similar statement holds with some logs. So you can compute how fast this blows up, and then you can just multiply with the correct prefactor of epsilon such that it stays exactly of order 1. And when you do that, then you can compute the limit. So first of all, there exists a limit, and the limit looks like this. So the limit, I think a square is missing. Yes, so sorry, there are a couple of typos in the slide. So this should, under the expectation, there should be a square. So I'm taking the same thing that was diverging before, and now I just forget the square, but otherwise it's the same thing multiplied by the correct factor of prefactor as a power of epsilon, and this converges to the L2 norm squared of the test function times some universal constant. Universal, I mean that it doesn't depend on phi; it depends on the modifier. Now, of course, now we recognize this as the variance of white noise. Of course, it doesn't mean that the limit is actually a white noise, but this turns out to be the case. So if I take this object, which was originally having a so now I remove the phi, and I just look at this as a sequence of random distributions, and this does converge indeed in low to a multiple of the white noise. Okay, so this is the first main ingredient even in the whole business. So basically, after the first Picard iteration, if somehow there is an epsilon prefactor to a correct power in front of the first, in front of the first nonlinear term in the Picard iteration, then that will produce us a white noise. Okay. Now, how does this actually appear in the equation? So there are two ways how you can enforce that this correct prefactor appears in front of your first nonlinear term in the Picard iteration. The first way is to put in the equation a prefactor in front of the noise. So in this first example, we take a full derivative of the spacetime white noise, which makes our alpha to be 1 less than the alpha of the spacetime white noise. So from -3/2, we go down to -5/2, which is certainly less than alpha C or alpha V. It's certainly super critical and violates the other condition. And now we put this prefactor epsilon to some power in front of this noise. And this means that after the first non-trivial step of the Picard iteration, a new white noise will appear as a limiting low. And it turns out that this persists for the whole equation. So what was proved relatively recently is that if you take the solutions of this equation, then there is a limit in low. So it's not like in the previous equation where the limit existed in probability, for example, or even in LP. If you make it if you're a bit more careful. So in this case, the limit exists in law. And the renormalization is a bit different. So there is still the additive renormalization in this with this C epsilon, but now there is a multiplicative renormalization in front of the noise, and the limit is you just recover the classical KPZ equation driven by a multiple of the white noise. There's a question?
Yeah. So here, so you're saying that this psi in the limit is only coming from the second chaos, right?
Well, it's a limit of guys in the second chaos, but of course itself then it lives in the first chaos.
Right. Yeah. So those higher order terms, they don't contribute to this psi.
No.
Okay. Thank you.
Now in a KPZ equation, there is actually, since the somehow terms are separated, there's another place where you could put a prefactor. So we basically looked at this independently of Martin, and were also kind of slower. And in fact, okay, but fortunately we looked at the different variation of the problem. So here we take, again, we take a derivative of the noise. This could be in principle any derivative which will be taken to be bigger than a quarter. So this D is again just you can think of it as Laplacian to the 1/2. In this case, the alpha is minus 3/2 minus gamma. So as long as gamma is bigger than 1/4, then the super regularity condition is violated, but it might still be subcritical. And as soon as gamma is also bigger than 1/2, then also it's supercritical. In this case, the limit is simpler, basically because somehow all the nonlinearity at the end vanishes, and the only thing that survives in the limit is the new noise. But this is actually a good thing to keep in mind, that the old noise also survives in the limit because there is nothing in front of it. And the two noise, so the noise that is produced by this second chaos and the old noise, are independent. In the previous statement, at least as written here, it wouldn't make sense of saying independence because anyway, it's just a convergence in law. But in this case, in the limiting law, both noises are there, and one can say that they are independent. And so just to reiterate, this can happen even when the equation is actually subcritical. Okay, so this was so far about KPZ equation, but somehow also in the paper of Martin, he kind of had a discussion making kind of a prediction. So I'm paraphrasing, so if something is wrong with this statement, then obviously it's my misunderstanding. But roughly speaking, it's saying the following, that whenever these two critical exponents are related in a particular way, namely that the scaling critical exponent is strictly smaller than this alpha v, which is related to the variance blow-up. So this equality has to be strict. Then this kind of phenomenon, which we see, so multiplicative type of renormalization and limiting in law, occurs for any alpha which is less or equal than alpha v. Okay, now at this point, I will start using some terminology from regulatory structures. So I hope I still can keep some some results free of too heavy terminology, but I will from time to time need to talk about models. So one important thing is I mentioned that there is this black box for regulatory structures, and when we do this multiplicative renormalization, which is suggested by this prediction, so actually Martin also writes down how the multiplicative renormalization should look, and this is exactly like this, again, not accounting for the logarithmic case when there's equality. So suppose that there is strict inequality in also in the alpha less than alpha v1. Then basically you should replace your noise by this noise. And this noise, of course, has a limit. This has a limit which is 0. And if you take the model in the sense of regulatory structures above this above this noise, the black box will not imply that this sequence of models converge. Basically, if it would, then the limit would be 0, because in the black box always implies convergence of BPHZ models, and the BPHZ lift of the zero noise is 0. Now, what is somehow different, or what is especially convenient for the KPZ equation, is that first of all you can do what is called the Pareto-Debye trick, which is what we partially, I mean, we've seen something like this in the argument before, namely that you start doing the Picard iteration, and then you look at, in fact, the remainder. So if you take the solution minus the first Picard iterate, then this equation, this remainder V epsilon, satisfies a nicer equation. And in fact, the equation that is satisfied by the remainder can be seen to be driven by two noises. One is the thing that is vanishing. So the original noise, which was this epsilon to certain power derivative of noise. And okay, whether here you put the hit kernel or not is kind of irrelevant, but okay, there's an important typo in the second one, so there should be a square in the second, so in the chi. So yes, maybe I will try to annotate, because this is kind of important. Now the question is, how do I annotate? Can I annotate my own? Well, if not, then I will just try to. Okay, I don't know how I can annotate. So then I explain in words. So in the Xi, in the Xi epsilon, we basically want to take the square of the zeta epsilon, but we treat this as a sorry, we take the square of the derivative of the zeta epsilon. But we treat this as a separate noise. So we look at the equation for V epsilon, and now we see it as being driven by two noises. And this pair of noises converge. Well, one of them converges to 0, the first one, and the second one is what we've seen before. This is the one that converges to a new white noise. And in fact, if you look at the BPHZ model above these two noises, then they do converge to the BPHZ model, to the BPHZ model over the pair of the noise 0 and new white noise. And actually, neither of these points is generally true for a general singular SPD. First of all, very often you don't have the Pareto-Debye trick, and even if you do, then this second point does not necessarily hold. So what we wanted to look at is, okay, can we have results that go beyond KPZ but do not rely, or go beyond in the sense that they do not rely on a special structure, but they confirm this kind of prediction of variance renormalization. So the kind of typical prototype of a singular SPD without a special structure, but with not too much singularity, is a two-dimensional generalized parabolic Anderson model, where the important point is that the noise only depends on space. And now we are in 2 dimensions instead of 1. Now, if you run the numerology, then the critical exponent is again -2, and the variance exponent for variance blow up is -3/2. So indeed, alpha c is strictly less than alpha v. So if you want to test the whole thing, then we would like to see a noise which is less than -3/2 regular. So for example, we could take a spatial white noise Xi. So now this is only spatial white noise, so it has regularity then -1. We take a derivative, it has regularity -2. And for this equation, we could prove the variance renormalization result, namely that, okay, then the result looks kind of like as before, with a couple of differences. So we take the the equation with the multiplicative renormalization with the epsilon 1/2, which is indeed the difference of alpha v and alpha. And we take the kind of additive renormalization as that's still there, which now, because of a nonlinear structure of this generic nonlinearity G, everything is a bit more has a bit more complicated interplay with the different derivatives of the G. And now we again get a limiting law, where the limiting law is another two-dimensional GPEM with a different nonlinearity. So first of all, we again see the prefactor C. So the white noise is multiplied again by a factor, but otherwise we do get a white noise in the limit, but the nonlinearity also changes. Now, to kind of say a few words about what is challenging about this is that, okay, since we don't have the Pareto-Debye trick, the only way, so somehow you cannot introduce really more noises that you would think of driving your equation. So at the end of the day, you really have one noise in your whole equation, which goes to zero. So in the limiting model, you have something that it's a model where it's a lift of the zero noise, but the model itself is non-zero. So in the rough path context, these are called the pure area rough path, where the path itself is constant, but the rough path component is non-trivial, which in particular implies that the limit is not a BPRZ model, so the whole BPRZ machinery is not something that's applicable, at least not in a simple way. Kind of what we've already seen before, that elements do not converge in a fixed state of chaos. Okay, this we've already seen. And what I also kind of want to emphasize is that there is no clean recursive structure like as in the KPZ equation. So we could try to do something similar as in the KPZ. So we could take that, well, we have two noises. One is, which I denote by the circle, which is really just the noise in the equation. And then I could look at the first Picard iterate, where the line just means basically convolution with hit kernel. So this is noise convolution with hit kernel multiplied by the noise again. This appears in the first Picard iterate, and this is what will produce as the new white noise, which I denote by this box. So I could try to think of the whole structure as being built from these two noises, but this is in fact not true. So for example, there is this tree, this ladder tree that appears in the equation, which will also contribute something non-trivial in the limit, but this is not obtained from the previous noises in any useful way. So if you of course it can be built from the circle itself by integrating, multiplying, and so on. But then, the circle itself goes to zero. So I don't want to use the circle. I want to use this dumbbell. But if I'm using the dumbbell as a building block and I'm only allowed to integrate and multiply, then I cannot obtain this ladder tree. And in fact, the convergence, this last convergence is rather tedious, and it's pretty heavy computation with Feynman diagrams. So this means that even in the simplest case, simplest test case, it's at the moment kind of challenging to prove this variance renormalization. And if you would want to go further, then at the moment, at least, I'm not aware of any technology that would allow you to do this. But there is actually one more example where we can say something, and this is the following, that in terms of scaling, the three-dimensional GPEM, which will be the next dimension, so the next, let's say, level of difficulty, is the same as the one-dimensional multiplicative stochastic equation, heat equation. So the left-hand side, as I hopefully somewhat explained, is at the moment looks very hard. But the right-hand side is very special because for stochastic heat equation, we have Ito calculus. And one can make another motivation for looking at this, namely to try to interpret the result of Heirer by Ito calculus, because at the end of the day, once you do Kohlhoff transform, it's a statement about E2 SPDs. So it's extremely, if you put in all the workhorses that make the result of Martin work, then it's a lot of input to say something about an equation that at the end of the day does not need so much machinery. So it turns out that in this particular case, so when we have when we are restricting our attention to E2 SPDs, then we can basically prove again variance normalization, which looks as follows. So now we take again, I want to take the derivative of the spacetime white noise in one dimension. But now I modify my approximation will only be approximation in space because I want to keep the Ito structure. As long as I keep the Ito structure, so this is just the heat kernel at time epsilon squared convolved in space with Xi. So now at the approximate level, I also have an Ito equation. In particular, I don't need any renormalization. And I have the same multiplicative factor in front, the same epsilon to 3/4. And basically, we can prove the same result as before. In fact, since we have this very special modifier, we can even compute the prefactor, which is some funny number with the fourth root of pi. But the change of the nonlinearity is the same. So even though it's a much more singular equation than the 2D GPEM, the change of the nonlinearity from the approximate equation to the limiting equation is the same. And so this basically gives a new proof of the result of Martin in the case of a spatial modification, modulo the Kohlhoff transform, and generalizes to the nonlinear case, which at the moment seems to be out of reach with regulated structures. So this is the end of the first part, and then I think it's kind of good time anyway to have that break, and I'm happy to answer any questions if there are any.
All right. Yeah, no, thank you for that. A nice first half of the presentation. So yeah, any questions from the audience?
Yeah, I actually have two questions. So for this result here, did you use a theory of regular structure, or you just use Ito calculus?
This is just Ito calculus. So this is a self-contained proof of 30 pages or so, so much shorter than any other result that was mentioned.
And did you use like the martingale approach, or?
We used well, I wouldn't say martingale.
Yeah,
so we used the mild
guess.
form of the solution.
Okay.
Yeah.
Okay. So my second question is regarding the two-dimensional parabolic Anderson model. Can you go back to here, just this page.
This one, okay.
Yeah, the one with trees. So for the one coming from the second order chaos, that tree there will be a space-time integral, right?
Yes, but since everything only depends on space, the temporal integral just gives you some constant. So the temporal integral immediately disappears. So you can think of this at the level of the trees, that all of your convolutions are only happening in space. The temporal doesn't matter for this one.
But I saw that it depends on okay, so you're saying that you integrate the time variable out.
Well, I mean, the circle itself only depends on space, right? And then you integrate the heat kernel against something that only depends on space. So then you can first integrate out the time variable, and this just gives you something. So then you don't have any dependence on time anymore.
But if I view it as a function, it's still a function of t and x, right? So you integrate your heat kernel from 0 to t, right? That's my understanding.
Well, not really from 0 to t. So you take very precisely you don't actually take the hit kernel, you take a truncation of the hit kernel, but then you don't cut off at 0, right? So when I said that this is really the first Picard iterate, then I was a bit lying, because for the first Picard iterate, maybe you would want to start from initial condition 0. Rather, you take this this cutoff hit kernel, but then you really convolve, so you don't put another indicator in your convolution, and then the temporal dependence immediately cancels out.
I see. So it's like a spatial random distribution converges to the spatial white noise here.
Yes. Yes.
Okay. Okay. Thank you. Yeah.
Maybe I had a couple of questions. So in this paper where Martin treats KPZ, I think there's also a rough path example, right? So I mean, how does the 2D GPAM, I guess it's a similar, am I right in thinking that the main thing about this dumbbell is that somehow the dumbbell has this recentering operation, right? That's what makes it different from the cherry. Is that the kind of same thing that is making complications in GPAM in 2 dimensions? Or is there new features in 2-dimensional GPAM that you don't see in the kind of rough path case that Martin did in the original paper?
Well, I think the rough path case, many things are, I mean, somehow simplified, right? Because, but yeah, just because that you only have 1 dimension. But yeah, to pinpoint really an essential or for example, you never have polynomial decorations, which is also, I mean, of course, I'm not claiming this is the most annoying part, but this is also something that is non-trivial. But as far as the convergence of the dumbbell, I mean, I don't think we of course first try to look at the argument about the rough path case, but it didn't seem to be very easily applicable. So there's somehow it's, and I mean this proof itself, the proof of this 4 noise guy itself is already tailored, as far as I understand. Maybe my understanding is naive, but to me it seemed that it was also tailored to the 1-dimensional case. So somehow the fact that you have an ordering between the time points made a difference there.
I see. Okay. Okay, no, thanks. Yeah, and I guess, I mean, would you say that the main issue with 3D GPAM is just basically systematizing diagrammatic estimates, or are there kind of more serious analytic kind of roadblocks that you encounter?
I think it would be the diagrammatic estimate would be, to my estimation, the hardest. So the analytic, I don't think it's automatic, but I would say that it's probably easier to automatize. But here we really did everything by hand, which is of course not feasible. So somehow some kind of systematic approach is needed, and somehow what is tricky is that this general criterions from Euler-Costal are somehow not, they just cannot work, right? Because you are not expected to have your kernels in the chaos. They will just not converge. So yeah. Instead, you basically, when you do these pairings, you will have a bunch of subgraphs which violates one of the conditions, and these subgraphs will converge to Dirac deltas. And then you want to somehow handle them in a systematic way, which seems difficult, but yeah, maybe possible.
Okay, no, thanks. Yeah, are there any other questions from the audience? Okay. Um, let's see. Okay. Well, in that case, yeah, we'll let you continue on the second half of your presentation.
Okay, thanks. Okay, so in the second half, I will talk about. So I will start actually from something that is at first sight not really related, and this is approximation of these equations. Especially I recently discovered, and going back to the, one of the classical motivation for many stochastic PDEs is this Parisi-Wu paper introducing stochastic quantization, and they in fact have this thing in mind that this whole approach of constructing measures via these SPDEs this approach is good because this can be used as a practical starting point for computer simulations. So this motivates that okay, then actually trying to have some kind of discretization or approximation of singular SPDEs is a pretty natural and fundamental question. And of course, there have been many works, and I collected some names, but I'm pretty sure that I missed maybe more names that I collected. So this has been looked at a lot, how to show convergence of various discrete approximations of singular SPDs. Typically, these are qualitative results that the certain discrete models do converge, or either starting from a discrete model or discretizing a continuum equation, they converge to the solution of the SPD, and then one can make. So these are typically rather technical and yes, tedious, and one can make it somehow even harder and try to ask what is kind of this with this thought in mind that maybe this somehow efficiency is a relevant question. So one can also ask whether this can be quantitative. As I will mention later, there is actually some kind of quantitative result that comes out usually from these works, but these are usually not particularly good. But okay, so already from this, it's kind of clear that this is a kind of tedious question. So what we will do is ask this question alternatively and ask the same kind of questions, so the quantitative, quantifying the convergence of approximations that are already well understood. So if we take approximations that are coming from these smooth approximations of the noise, whether for these approximations we can prove good quantitative error bounds. And the important analogy why I don't think this is so much cheating is that the important feature that both of these kind of approximations have is that both of them don't see below a certain scale. So both of them have a kind of a discretization scale under which they don't see what happens. And so from this perspective, let's say the big picture goal is what kind of error do we make by failing to resolve these small scales. And so we choose to try to answer this question for the simplest approximations that we have, instead of going to the actual discrete approximations. So let me first state. So as I mentioned, actually the existing result already for discretization, but certainly for the smooth modifier approximations, they do provide some kind of rate of convergence, which is almost fits on a slide. I mean, there is some some things which are not quite automatic, but okay, fairly convincing and essentially correct argument is the following. So there are a couple of ingredients. The first one is that if you take any distribution f, which is in C alpha, and you modify, and you ask the question, what is the error that you committed, then it depends on where you measure the error. So if you sacrifice error, if you sacrifice by regularity gamma, then the error will be of order epsilon to the gamma. Now this actually has a slight caveat. The modifier has to be fairly sufficiently nice for this. But for example, as long as gamma is less or equal than 1, then for any modifier this is true. For if you want gamma bigger than 1, then certain symmetries are imposed, but this is a minor caveat. Okay, so this is true for any distribution. The other ingredient is that how the black box, a bit more detail about how the black box actually operates, or what the black box actually outputs beyond just the the convergence of the solutions. So the black box actually outputs a bit more, and this is the following: that if you take the noise to solution map, where the noise does not simply just mean the noise itself in the equation, but involves these higher order trees. So in the case of the KPZ equation, so again, also in this error, for this error question, I focus on the KPZ equation. So you have to put in your data the higher order Picard iterates coming from your noise. So the first one would be this cherry tree, which is basically the thing that we wrote down by formula before. So this red line, before the lines were just convolution with heat kernel, the red line is convolution with derivative of heat kernel. So this is the first nonlinear term that appears in the Picard iteration, and then if you keep iterating, then you see this tree and so on. And what the black box actually provides you is that the map that takes in these noises and outputs the solution is not just well-defined, not just continuous, but it's actually local ellipsis continuous in the some correct topology on the trees, which is the following. So you take a regularity exponent for the noise, which has to be lower than -3/2, because -3/2 is what the spacetime noise has as regularity. And then the next order guy has to be of regularity -1, -2 kappa. So somehow you just do the power counting by adding always 1 when you have a red edge, and you add up the regularities always when you have a product. And there's something in the chat. Okay, just someone's leaving. Okay, okay. Yes. So as long as basically these irregularities increase, which is essentially just the subcriticality criterion, then the solution, this noise to solution map, is local ellipsis continuous. So then kind of we want to put these two ingredients together. So that would be the third ingredient, which is not really automatic, but actually one can make it work. So one could hope that as long as I can lift my noises into this space, so this is what is referred to as the space of models, and I know that I can lift the noises as long as the two main criteria that we saw at the beginning are satisfied. So as long as I can lift these noises to this model space, then actually also I can lift them in a way that the error bound that I have on the level of the noises, that this persists for the lifts themselves. Yes, so Then, kind of putting this together is a first guess of an error estimate that one can somehow extract from the black box if one is careful, and that is the following: that as long as the gamma, which will be the rate that I'm aiming for, is such that the alpha minus gamma is still admissible noise regularity, so it's still subcritical and superregular, then the error can be bounded by epsilon to the gamma, right? Because if from the noise I can go to the model in a sort of Lipschitz way, I mean Lipschitz in a certain sense, then from the model to the solution I can move deterministically Lipschitz way. So then the error that I had in the first line persists also for the solution. So this gives you the first guess of what error you can get for in the case of KPZ equation would be epsilon to the 1/4 minus something. So just arbitrarily close to minus 1/4. Okay, so one can make a better argument, which goes as follows. And this, yes. So the first observation is kind of trivial, is that if I want to prove an error bound of order epsilon to the gamma to the difference, then I can just rescale the difference and aim for an order 1 bound. I do this because now I write the system of equations satisfied by h epsilon, and this rescaled error. Now, when I write the system, I ignore all renormalization business, which is, okay, not trivial that this can be ignored, but for now, let's just ignore it and let's try to get something out of this argument. So the equation for W epsilon, so this rescaled error, is now an affine linear equation in W. Yes. So in terms of W, you right. So when I take the square, a squared minus b squared is a minus b times a plus b. That's the deep theory here. And then the noise that drives the W epsilon equation is the rescaled difference of the noises. Now, from what we've already seen, we actually can say something about the regularity of this guy, namely that this this thing stays order 1 in a certain regularity, namely when I lose the regularity gamma that I have in terms of epsilon here. This was the previous ingredient one. So now what do I have? I have a system of equations which is driven by noises of certain regularities, and these noises are of order 1, which means that by the black box, the solution is also of order 1, as long as there is a solution, as long as the system actually does fit into the black box. And that is actually what we are going for, right? So we want that W epsilon is of order 1. So then now we want to check that the black box can be applied. Now this system is actually whatever I choose gamma is always subcritical. Notice that the gamma does not change the regularities of the original noise. Originally, this was a subcritical equation because this was just KPZ equation. And so the way you can think about why the first point is true is that if I give a new name or a new symbol for this noise, then all the trees in the big system, so a new symbol for the eta epsilon, then all the trees in the new system look like trees from KPZ, except at most one noise node, I replace the noise by the eta epsilon. But this just means that all of the regularities are shifted by gamma below, but subcriticality in the terms of the regularity of the trees means that the set of regularities is bounded from below. If I shift something bounded from below, then it's still bounded from below. So this is actually always subcritical for any gamma. But the superregularity condition does not always hold. And for the case of KPZ, it holds as long as gamma is less than 1/2. You will see why it's so okay, I didn't really write the conclusion, but the conclusion of this is basically as long as my transformation and this kind of formal way of deriving this system, which again completely ignored, for example, renormalization, as long as all of this was correct, then this argument already gives you actually an error bound of 1/2 instead of the 1/4 as before. Well, not quite 1/2 because it has to be less than 1/2. And when gamma equal 1/2, then it is the point where we kind of connect back to variance renormalization. So then the superregularity condition fails. But actually, something similar happens as in the first part, namely that the first Picard iterate in the W equation produces me a new white noise. So the first Picard iterate in the W equation is this product. So the second, okay, let me go back to the nonlinearity of W. So the nonlinearity of W is actually linear in W, but W, the spatial derivative of W is multiplied by the spatial derivative of H. So I have to take the linearized solution of W, which is this epsilon to the minus 1/2 xi minus xi epsilon noise, and multiply by the first Picard iterate of H. And this Vig product converges to a new white noise. And from this, one can, okay, basically on the basis of this, one can say the following, kind of sharpening of the previous argument, which is somehow makes it quite sharp. For simplicity, I don't say error for H minus H epsilon, but rather I compare H epsilon and H epsilon half. So I compare comparable dyadic scales, but then you can do some kind of dyadic argument. So for simplicity, I just write it like this. So if I now look at the H epsilon and H epsilon half and the rescaled version of the error, then first of all, this remains bounded in LP of omega, and it has a limit in law, very similarly to the results in the first half, where the first two coordinates are, of course, just copies of solution of the K-Pizza equation, and the third component is this limiting W. So the limiting W basically solves the W equation with a new white noise. And again, in this system now, both the old white noise and the new white noise appears, and the W then solves a fine linear equation driven by the new white noise. So this, for example, first of all, it tells us that this endpoint rate 1/2 is achieved, but it also tells us that it is optimal because if I rescale by this epsilon to the minus 1/2, then I get a non-trivial limit, right? So it's kind of clear that the limit of this W is something non-trivial. Now, of course, I've said a lot of things under the rug, just to mention a few. So the fact that the renormalization stays consistent is not a given. The fact that my new noise is actually rather singular, so it is below singularity -2, which is actually kind of a threshold for multiplying with indicators, which you have to do if you want to put it in a Duhamel formulation. And maybe most importantly, just the fact that I have convergence of the noise, as before, is not automatic that it implies convergence of the models. And some or all of these points can be quite tricky for other equations other than the KPZ. So this is why for now we just, let's say, confident in the KPZ case. But I have a couple of examples where one can kind of guess what the rate would be from the very naive computation and what would be in with this refined argument. The color coding means, okay, the green is that we can really prove it. The slighter green means that we think we are pretty close, and the orange one means that we are, I think, pretty far from a proof. But the guess is actually, I think one can be pretty confident from the about the guess, because the guess is basically just uses this line. Right? So the guess is to determine the rate is what is the exponent that gives you this non-trivial limit in the at the level of this first Picardie rate. And for example, what's interesting is in the barely singular cases. So for example, in 2D PEM or 542, you have logarithms appearing in the sharp rate. It's not that the rate itself is a logarithm. The rate has, for example, in the 2D PEM case, it's a rate 1, but actually it's a bit worse than rate 1 because it's multiplied by a log. And the same is for 542, but with some different power of the log. And for other equations, like for 543, if you run the naive argument, you get a rate which would be 1/3 and cannot really reach 1/3 with the naive argument. And with the refined argument, one can get an error bound of epsilon. But again, this is kind of this is more conjecture than proven. So that was the second half, and thank you for the attention, and I'm happy to answer any further questions.
All right, so let's thank our speaker for a very nice talk. Yeah, any questions from the audience? So you can use the chat, or you can just kind of unmute yourself. Either is okay. Yeah, I had a question. I mean, maybe a naive question, which is why is 543 harder than KPZ? Or what's the kind of thing that's shakier about 543 versus KPZ when you're kind of formulating these conjectures?
Well, so first of all, the second point is already quite tricky for 543. So you, okay, let me see. Now I will try again whether I can annotate, but if I didn't manage the first time, maybe I will not manage the second time. Yeah, so yes, for example, this is also already something that's, okay, this I don't expect to be a huge obstacle, but it's a non-trivial obstacle that already you will get a white noise in the limit. And this white noise, you will get this cherry, which is actually a triple cherry. But this white noise is already below the -2 threshold. So the fact that this one actually converges also in the same rate if you multiply with the indicator is not actually so clear. But okay, the first point, I think we would be pretty convinced that the renormalization stays consistent. So what I mean basically is that when I say, yeah, this I didn't comment that much. So whenever I say solves in a blue, it of course means that these are all singular equations, so they all have to be renormalized. So, but on the other hand, H minus H epsilon solves an equation when I already have a counter term. So I have to be consistent that the counter term that I have from H minus H epsilon is the same as the counter term for the W epsilon equation just by applying the theory. Okay, this part I think we can do, but the convergence of the models is again quite a bit trickier. So so for example, already at the level of the first type of results, already this one would be actually, I think, trickier for 543. The reason is that, okay, if you want to treat the things that converge to a new noise as a separate noise, so you basically treat certain blocks as not trees, but just one block itself. And then when you have to extract subdivergences, you're kind of not allowed to take part of this block.
I see.
And this for the KPZ somehow doesn't really matter, but for 543, it actually matters. Yeah, this would be an answer.
No, thanks. That's clear. Yeah. Yeah. Any other questions? Let's see. Okay. Okay. Well, if there are no more questions, we can thank our speaker again. And oh, Constantine, you have a question or no? Okay. And as always, we'll post a YouTube video of this talk online. And we are planning to do more talks during the summer than we originally planned to. So we will likely have an upcoming talk in July. So you'll see an email about that soon. Yeah, and otherwise, yeah, have a great summer and thanks everyone for coming.